Next section I want to talk about maybe a little different topic. It's not so much material dependent as test dependent, but it's very important in the use of ceramics because of their sensitivity to rapid changes in temperature. And of course, for many people, this is the way that many ceramics fail because they were quenched too fast. You put them in cold water when you shouldn't have. You pulled them out of the oven, set them down on a cold surface. But there are lots of ways in which thermal stresses can occur in ceramic materials. So I thought I would take the time and just briefly discuss kind of where we are in our knowledge of thermal shock and maybe a little bit about a testing procedure that might help to determine the thermal stress resistance, thermal shock resistance. In part because it's so particularly important for this class of material. So first of all, in many cases, if you see a failure in one of your parts, you can tell that it's thermal shock failure, thermal stress failure, because of the wavy nature of the cracks emanating from the failure source, which is in here. Again, when you become familiar with doing fractographic analysis, it becomes easy to see. You follow the macroscopic crack pattern back, and you find that the origin of failure will be in here. You can look closely and see what that origin was, but the macroscopic themselves are wavy in nature, and this gives you some idea of that this might have been a thermal stress failure. The stress fields, the reason is that stress fields are non-uniform, so you get this kind of wavy crack pattern. What's been known for a long time, if you do a thermal stress analysis, one of the fathers of modern ceramics, King Rhee in 1955, was one of the first to analyze thermal shock in ceramics. And you can see on cooling and heating you get different conditions. If you cool rapidly, then you get tensile stresses on the outside surface of a part that you see here, and the internal portion is in compression, and the opposite is true during heating. You form tension in the inside and compressive stresses on the outside. So this can lead to two different kinds of behavior. And he derived an expression that it's just a general expression for thermal stresses, that the stress on the surface, that surface stress that we talked about, we'll talk only about cooling in this case, is related to the elastic modulus of the material, thermal expansion coefficient, Poisson's ratio, and the temperature differential from which you cooled. So T0 is the temperature from which the material is quenched, and T is the surface temperature at some point in time. So this is a general expression for the thermal stress development in almost any shape or size or material. You see it has material parameters in it, but these are probably ones that are pretty well known, thermal expansion coefficient and elastic modulus. And there are a whole series of expressions for this kind of stress depending on the shape of the material, because that will affect the way in which the stresses are developed on the outside surface. But there's an additional complication which causes a real problem in understanding and measuring of thermal stresses, and that is the fact that the heat transfer coefficient between the part or the specimen that you're cooling from some high temperature to a low temperature has a significant effect on the stress development in the material. So the previous expression really assumed that there would be almost instantaneous heat transfer between the part and the cooling medium, but the actual fact is that you see here, there is another parameter, notice the Biot number, beta, or Biot modulus, which is related to the heat transfer length, the smallest dimension of the specimen that you have, the surface heat transfer coefficient, which is typically very poorly known for most materials, and the thermal conductivity of the material itself. And this parameter, this Biot number, has to be factored into any prediction calculation of what the thermal stress or what delta T I can stand in any material. So if the question is at what delta T, at what temperature differential will fracture occur, then again I'm using that same expression. Now I've put in the beta as well as all the other parameters I showed you earlier, and then I rearrange the terms to calculate what delta C will be, and you can see that it is directly related to the potential, the strength of the material, which I can measure independently, elastic modulus, thermal expansion coefficient, but I also have to bring in that Biot modulus, which contains thermal conductivity and heat transfer coefficient and size. So here's the real equation that I have to work with to understand the critical delta T. In other words, when am I likely to fracture apart due to rapidly cooling it? And just to go further on this then, that Biot number has such a significant influence. When it's small, there's almost complete insulation. Stresses are low. So for small parts and high thermal expansion, high thermal conductivity, I don't have to worry too much about thermal shock. When beta is large, the thermal stresses can be significant. And I could go back to a previous equation where you can see that. So, for very small parts, that delta T, this number is small, delta T is very large. When K, the thermal conductivity of the material, is very high, this number is also large. For many ceramics, though, that is not true, and the delta T under which I must work is, within the 200 to 500 degrees centigrade. So this is the right equation. Our problem is that it's very hard to determine what some of the values of these parameters are. Heat transfer coefficients are poorly, if not known at all for most materials. Thermal conductivity is known. But so the conditions under which you quench, which will determine the heat transfer coefficient here, are going to make a big difference on the delta T at which failure will occur. So the rest of the material parameters I can measure, but that's one that I'm going to have to be cautious about. So how do we go about doing thermal stress or thermal shock testing? Well, first of all, you need that strength of the material. So you measure the strength of a set of specimens. And you could do it uniaxial or biaxial flexure. Then you take another set of specimens, you heat them in a furnace at some temperature until you get to equilibrium. You quench the specimens one at a time into a liquid. Usually room temperature water. There's recommendations that slightly heated water works better, but the heat transfer between the water and the specimen makes a big difference in the thermal shock resistance of the material. And then you measure the strength of the quenched specimens. And there is guidance on this. So ASTM standard, you see here, provides some detailed guidelines on how you do these kind of tests. One has to be cautious, though, because if you're quenching in water, and in the real life, the medium that you're working in is not water, you have to be careful that you're not getting misleading information from the water quench. It doesn't always transfer from one kind of quench medium to another. And so the kind of data you typically see that after you do this is that when you reach a certain delta T, you will get a certain decrease in strength. It can be a gradual decrease in strength as the temperature difference increases that you see here. It could be a sudden drop in strength that you see in here. It depends on the material itself and the quenching medium and so forth. So just to point, this is a useful but not a completely exclusive test to determine whether I have a material that is going to be quote-unquote very thermal shock resistant. But I think it's important to talk about it because, again, thermal stress failures are such an important aspect of ceramic materials. And of course, if I do this repeatedly, I could take the same specimen and re-quench it, and there can be further crack growth. So you have to understand, if I do the same material, I quench it once, I produce some stress and the crack could have grown a small amount. I do this again, the crack can grow larger. And finally, if I keep quenching the same specimen, it's a good chance I will lead to failure after numbers of thermal cycles in these kind of tests. I want to point out some other considerations before I finish. If you're quenching from high temperatures, you got to be careful that you don't get radiant cooling of your specimen when you take it out of the furnace before you put it in the quench medium. In other words, you think you're at 800 degrees C, but if you wait too long to put it in the quench medium, you might be at a different temperature. I mentioned earlier, quenching in a little higher temperature water than room temperature gives more consistent results, and there's references at the end to some of those studies. And the thermal properties of the material play a major role in determining thermal shock behavior. So I think that's shown up in the equation, and that equation seems to hold for most materials. And also, I didn't talk about rapid heating, but quenching from elevated temperatures won't necessarily yield the same results as rapid heating to that temperature. So when we talk about applications such as gas turbines, I can get thermal stresses developed during heating up a gas turbine blade, for example, but quenching that same blade from elevated temperature may not give me the right information as to what might happen in heating. So there's a lot more details than I can give in this length of time, but I thought it worthwhile pointing out what some of the basics are about thermal shock testing and give a few pertinent references to this topic.